Next, we're going to use the Biot-Savart's law to find the magnetic field due to the current in a segment of wire. So let's remind ourselves what the Biot-Savart law was. So it says that the magnetic field at some point P, whose position is given by the vector, say r, is given by the integral over sources, over the current source, and there's a constant factor which is given by mu naught. This is the permeability of free space divided by 4 pi, and then we have the current times the current element cross with the unit vector that is pointing from the current element to the point P divided by the distance squared. So this is Biot-Savart's law. So let's look at a concrete situation. So suppose that we have a wire carrying a current. So we have a wire, it's carrying a current, and we have some point, say, outside the wire, and we want to find the magnetic field at the point P. So the wire, of course, can be connected to some external circuit, which is, say, providing it with some current, but we are not going to be interested in the magnetic field due to that other part of the circuit. Okay, so how do we do this? So to see how the Biot-Savart law will let us calculate the magnetic field at point P, let us isolate our wire. So let's redraw our wire over here. So this is the wire, and here is, say, our point P. So let us introduce a coordinate system. So we have a coordinate system which goes like this, and this is going to be the I hat direction, and this will be the j hat direction, and the z axis or the k hat direction will be pointing out of the plane of the screen. So let's consider a small segment of the wire over here. So this is going to be, say, ds, the vector, and the current flowing through this wire is going to be, of course, I, and let the integration variable would be the position of this current element. So the integration variable is going to be this thing. It'll be x prime. We also denote the position of the point P by the coordinates x and y in our coordinate system. And we're going to assume the z coordinate of the point P is 0. So now let us look at the relevant quantity. So we need the distance because, according to the Biot-Savart's law, we need the distance from the current element. We need the distance from the current element to the point P, as well as the direction. So the distance is going to be, given by this, and this is r, say ds comma p, and the distance from the origin is going to be given by this thing, and this is vector r. So this is the vector r. So let us introduce the length of this wire. So suppose this wire is, its length is L, then the x coordinate of this point is going to be minus L by 2, and this will be L by 2. And let us introduce the vector r prime to be the position of the element ds. So it's given by x prime times the unit vector I hat. Right. The distance that we're interested in is r ds P, and that will be given by the modulus of the vector r minus r prime. As you can see, this is the vector r prime, and here is our vector r, and therefore this is going to be the vector r minus r prime, and it's the length of that vector which is given by this distance. And we also need, for Biot-Savart's law, this direction. So this direction is going to be given by r hat ds comma p, and that is going to be given by the vector, which is r minus r prime divided by its length. So r minus r prime, the length. And now we can evaluate this explicitly. Recall that r, the position of the point P, by x times the I hat vector, y times the j hat vector. And therefore, this thing is given by, in the numerator, we have x minus x prime times I hat plus y j hat, and in the denominator we have the length of this vector, which is given by x minus x prime whole squared plus y squared, and the whole thing is under a square root. So this is the r hat vector. And the other thing we need is that for the Biot-Savart's law is that we need to know how the cross product of these two things is going to play out. So here we see that ds is pointing in the I direction, and and then we have in this vector both I and j, so there will be a cross product between I and j. And let me remind you, the cross product between I and j is given by k. So now we can plug in all of this into the Biot-Savart's law and figure out what the magnetic field is going to be. So the magnetic field at the point P, whose coordinates are given by x and y, is going to be mu naught by 4 pi. This is the constant part, and there's an integral, and then inside the integral we have the current, and then we have ds, the vector ds, but the vector ds we know is given by I times dx prime. So we will have here, let's just write, say, dx prime, and then after that here we are going to have dx prime times I hat, and that's going to be crossed with the unit vector, but the unit vector involves r minus r prime. So we are going to have x minus x prime I hat plus y j hat, and then in the denominator we'll have now 3 powers of the length of this vector. So we are going to have x minus x prime whole squared plus y squared, and here we are going to have 3 halves, and the integral will be from minus L by 2 to plus L by 2. So this looks like a forbidding integral, but we can use an integral formula to evaluate this. The formula that we will need is the following. It's the integration of dx prime divided by, say, x minus x prime whole squared plus y squared, the whole thing under the power of 3 halves, will give us minus x minus x prime divided by x minus x prime whole squared plus y squared square root times 1 over y squared plus c. So, but of course we're going to evaluate it as a definite integral. So if you do this and plug this into this formula, of course in this formula we can factor out I because it's a constant, and we can also factor out y. We can also factor out, say, y, because that is also going to be constant. The other thing is that we know that I cross I is 0, so the first term is not going to contribute anything. So it'll be the second term which will contribute something. So what do we get? We get b x y is going to be given by mu naught I divided by 4 pi, and then there will be, so there's a y in the numerator, and after the integral there will be a 1 over y squared, so these two guys will cancel to give me 1 over y, so there'll be a 1 over y over here, and then we can factor out this minus sign. So this minus sign is going to give us a minus over here, and now the rest of the thing we are going to get for x minus x prime, we are going to get x minus L by 2 in the numerator, and in the denominator we are going to get x minus L by 2 whole squared plus y squared, and the whole thing would be under a square root, and then we are going to get for the lower limit we are going to get x minus L by 2, so that's going to be x plus L by 2, and in the denominator we are going to get x minus L by 2, that'll be x plus L by 2 whole squared plus y squared, the whole thing under square root. And that is our final answer for the magnetic field at the point P due to a finite wire carrying current. And of course we cannot forget that this has a direction, so it's going to be in the direction of K because of the cross product over here between I and J. We are going to have the resultant vector in the K direction. So once we have derived this, let's look at the limit in which this wire becomes infinitely large, so that L goes to infinity. And then what is the field, magnetic field, due to an infinitely large wire for a point P which is close to the wire. So we are going to take the limit in which L goes to infinity, that is L becomes much larger than x and y. So if you do this, if you look at this formula, what we see is that in the numerator, this part, the x part, will not matter, and this part will not matter because L by 2 is much larger. And of course there's a minus L by 2, minus L by 2, so they will add up to give me, because the denominator will be the same in that limit, that they will add up to give me minus L, and that minus will cancel this minus, and we will get a factor of L out. In the denominator, we are also not going to get L, this x is not going to be relevant, and this y is not going to be relevant because L will be much larger. So from the denominator, we are going to get L by 2. But that 2 is going to go into the numerator, and that will cancel with this 4 to give me 2. So in the end, we are going to get, in that limit, we are going to get B is going to be xy will be given by minus mu naught, and as we said, this minus will become plus, and then there's a current I, and because of the factor of L by 2, that 4 pi will become, say, 2 pi, and then we already had a factor of y before, but all the other factors of L now cancel out, and we have the direction K. So this is the final result. Of course, we are assuming here that y is not equals to 0. So let's just recap. So if this is an infinite wire and there's current going in some direction, say I in that direction, and we're looking at some point P, then the magnetic field at that point P will be given in the direction coming out of the page. But if the point was in the negative y value, if the point was over here, if this was P, then we see that the magnetic field would be pointing into the page. And that's because over here the value of y is negative, and therefore that minus sign flips the direction of k. So this is the answer that we get from Biot-Savart's law.